right, so all of the information for your final project is posted. Make sure that you are on top of that. The first due date is this Monday. What is the date this Monday? So the 24th is your proposal is due. So if you haven't gotten that approved, make sure you try and get that approved quickly. If you've gotten verbal consent, just make sure you're finishing that up. On Wednesday of next week, for every section, is going to be due your testing. So this is testing which you're welcome to still use the testing you already did last class, half the semester. So if you're using the same actuator, the same LED, the same sensor, whatever you're using, if it's the same as what you already tested, you don't need to retest. But if you haven't, or if you're using something new, you want to just make sure you go through that process of like, okay, this is one extreme, this is the other extreme, this is somewhere kind of in the middle, and maybe testing it in different environments, locations, with different weather, depending on what exactly you're trying to achieve. So thinking about for your project and what you want to achieve from it, what would be something you could make a variation to make it more robust? So this is going to be your testing. It's going to be also your design and simulation is needed by Wednesday. So those three need to be done by next Wednesday. And then the final checkoff, you're going to have 3 opportunities. One is on the following Monday after Thanksgiving. You will be able to check off during the lab time. I can't remember what time it was. What's the lab time on Mondays, do you guys? 3 to 6, okay, thanks. It's like trying to remember, 3 to 6. Wednesday, December 3rd, there's a 7:30 to 10:30 a.m. And then you can also pass it off right before our optional final. So if you want to meet in my office, I'll be there from 12:30 to 1:15. And then also after the final exam period time, I'm also willing to check you off at that time. Tyler has very kindly offered to give an extra checkoff time that wasn't posted on that on Saturday, and that would be from 12 to 4:30. So if you haven't checked it off before then, that would be another opportunity to check it off. So do make sure you're finishing that off. Any questions about the final project? Yes.
If we already got it approved, do we still have to show up on those days in December?
So if you've gotten it approved, you still need to do the simulation in person. So you need to be showing up to lab. If you've already checked off and finalized it, you do not need to go to lab.
Okay.
So if you've finished the full amount of everything and shown your actual breadboard and had it debugged, then you're good to not show up anymore. So if you get done early, great. Then yes, don't need to worry about going to lab anymore. All right, any other questions, comments? Has anybody finished yet? Okay, so quite a few of you actually finished the full project. Okay, great. So if you're done early, great. Just make sure you are submitting all of what you need to submit for the final grading. So any other questions, comments on that? Yes.
So I am making my proposal right now, but I have my lab later today.
Yeah.
And so for the simulation, I might not be able to work on it because I'm waiting for the check off of my proposal after it's done. Do I need to go to the lab today if the simulation is due physically like on Wednesday next week?
It's due by Wednesday. So if you want to chat with the TAs and get approval right now and then work on your simulation today and get that finalized, that's great. So you can also go to lab and just, a lot of it can be just a very quick, yes, that sounds good, go for it. Okay? All right, yes.
Would it be great
What about the 250? Sorry.
Are we gonna be graded against those?
What do you mean against those?
Like, is that factored into the whole 100% legacy?
No, no. It should not be calculating in there. It should be an additional amount.
It's calculated right now as a third exam, but once you do the third exam,
Ah,
then it'll like not be required.
okay. Yeah, so it's bumping in there because you have a 0 on your third exam.
Okay.
And so, yeah, it will override it basically once you have it, and then it will be, because then you'll be over 100% possibly. Right now you're not, because you're missing that third exam. That makes sense. Thanks, Shazan. But yes, in the end, it shouldn't, but right now it might, just because you haven't fulfilled that one yet. Okay. There is a quiz that is going to be due, and I had told you guys that it would be due Saturday night, so it's due by tomorrow night. So it is on, now I'm trying to remember what it is. So it's a circuit in the complex domain, and you need to do node voltage, I think, to solve it. And you can use a calculator. You can use an online calculator for this one. This is just to verify that you can get a solution with it. So do make sure you've been able to do a lot of the problems that we've done here in class. As long as you're able to follow that and do those problems and get the right answers, then you'll be fine with the quiz. So again, that's due, it's open right now. It was open yesterday, and so it is open until tomorrow night. So do make sure to do that one. Okay, so we're moving into chapter 12. And on chapter 12, you have sections 1.2 or 0.1, 0.2, 0.3, 0.4. All of those, I just want you to have a high-level understanding of what's going on there. You don't need to know all the details of the math that's going on there, because a lot of you may not have seen that yet. And so I want you more to know the concept of, one of the things is in 12.1, it talks about this delta function. So I want you to understand what these functions are, because they're very, very useful when we talk about modeling and using a mathematical expression for what's going on in real life. And so I'm going to go over that, which is what I do want you to understand from it. The other parts of it is understanding just like, okay, I'm moving from the time domain into the frequency domain. To do that, I can use a few different methods to do that. One is the phasor that we've been talking about. The other is called the Laplace transform. And it, again, is another way of transforming from time domain into that frequency domain. The last one, which we're not going to talk about here, that you'll talk about in 3500 for EE students or CE that take it as an elective, is going to be in ECE 3500. You're going to talk about that Fourier transform. All of them do the same thing in that they're moving you from the time domain into the frequency domain. Once you're in the frequency domain, any of those methods make it way easier for us to add, subtract, multiply, divide, instead of taking a differentiation and an integration and making it a fifth order circuit. You know, that makes it very hard to solve those. So all of those. And then the next method is to go, once I have a signal that is a frequency domain expression, it can be either in j omega kind of form, so that complex form, or what we're going to talk about today is we can also do it in the form of S. So those are the two ways you're going to see it in the frequency domain. So far you've been seeing it with j omega or with j times some number. And so that's what we really have been doing now. And so we're going to move now to look at, with S, it's actually way easier in my opinion. So we're going to look at this method, and then we're going to have then this new S variable. Then we're going to look at just analyzing using the same methods that we've been using. Okay? So that's what you really want to take from chapter 12, and most of the focus is going to be in 12.6 and 12.7. So 12.6 is going to talk about the transform from the time domain into the frequency domain for our elements that we know. So we'll get to this using S in a second, but as I said, for 12.1, there's two different signals that, as I mentioned, are really useful to use. So when we're sitting there and we have our circuit on the breadboard, we haven't hooked up the power to it yet. It is just, there's no signal on there, so everything would be 0 on there, unless you actually physically charged up the capacitor, or accidentally maybe it charged itself up and then you put it on. But those are things you don't really know if it was accidental. So most of the time you're gonna look at something and then all of a sudden you're gonna put power onto the circuit. This is the mathematical expression that we use to model that. So instead of using a switch, we can just mathematically express it with this function. This is called the unit step function. And when you use this multiplied by, say, 9, so say I have a battery 2, or however many to make 9, 4 AA batteries, that gives us 9 volts. And we express it as 9 volt U of t. That means that it is going to be this exact graph with the amplitude is 9, and then it's 9 once I've turned it on. So that just models me having it off and having it on. So we use this U of t. Why this is important is then in the Laplace transform tables, Fourier transform tables, you're going to see now this expression that is going to be used and transformed in from the time domain into the frequency domain. So it's really important for us to know how do we model that mathematically. So this is what we do to model that. Any amplitude that it has, so let me do cosine omega t times u of t. So even if we have a sinusoid, and again, we haven't hooked the function generator up to our circuit, I can then express it by this mathematical expression, meaning that yes, it was off at one time, and then at whatever term whatever I consider as time 0, I plugged it in, and I've hooked it up to the circuit. So this just means that before a time of 0, it's going to stay 0, and then at 0, it then starts to give me a cosine. So this would just be cosine omega t times u of t. Does this make sense how to use this unit step function? Yes?
Is that thing supposed to say t even less than 0?
Oh, yeah. I love the... Thanks for pointing that out. That should say less than 0.
I just got confused, so.
Yeah, no, sorry. I copied that, I didn't even check that. So yes, time less than 0 is 0, and then after it's 0, you have the value. So this is the value is that and equals to 0. So when it equals 0, you're at your value of whatever the function is. In this case, it's 9 volts. All right, any questions about using this unit step function? So we've talked about that with other things, that when we have, a real system, we want to model it with components that we know or an expression like we know. So this is one way of modeling this. All right, the other one is where in a signal, you might have something that kind of looks like this, and then it goes like this, and then all of a sudden you get something that kind of looks like a spike. This is very common in what you're going to see. And so in these spikes, you're going to model this spike by this function. So how we model this is we assume that this is a really small, narrow area, and the y value of this, if this is 10, and your time value here, say it's 20 20 seconds, that happens. You would say that this is 10 times, and this is called the Dirac delta function. Or for us in engineering, this is the same as the impulse function. They mean the same thing for us. In math classes, they mean a little bit different things, so I want to clarify that that's for engineering, is we assume that that means the same thing. The impulse function or the Dirac delta function is the same thing. So if you remember from shifting of a signal, this would just be delta t minus 20, and that's because it's shifted to the right. And the value, the amplitude of it is 10. So that would be this. So that's why these are 1 in front of it for both of these. And again, this is a very common one where you have a spike kind of a thing in your circuit. So a lot of times these will be really big spikes, and so, you know, it wouldn't be 10, it would be like 1,000,000, you know, or 100. When you have a 9-volt battery and you get a spike, or if you're on, most of the time you're gonna see these on power, like something that already has something on it, so like the wall outlet may get a spike in it. Or another system where it's kind of tied to other things that have a higher possibility of generation of it.
Is this what a surge protector does?
Yes. So a surge protector protects you from these spikes that come in from your wall outlet signal. So what happens usually on that is that you have something has happened, you know, whether it's a tree fell on a line, and you get like this big pull of power all of a sudden to there because it has this big disconnect, and then it kind of creates an arc fault. And so you'll get a big draw. And so your surge protector actually uses a diode most of the time, turned backwards so that that current can't flow back in. And then it has a rating on it, which if you've heard of, I don't know, you guys are young, but older appliances used to have fuses in them, and some of things still have fuses in them, where your fuse does the same thing. Well, it will protect it from, once it hits some rating, it will pop, and then it won't allow the current to flow anymore. So any other questions on these two functions? Okay, so you want to know, and again, the delta function or impulse function is something else you're going to see very commonly in the tables, transforming from time domain into the frequency domain, either a Laplace table or a Fourier table. All right, so you want to make sure to understand these two functions and how to like look at a signal and actually write them. So here is an example of the Laplace transform. So the Laplace uses this squirrely L, and that means that it's transforming it from time into the frequency domain. So here you would write that this value is equal to the Laplace of the Dirac delta function. And that just equals 1 in the frequency domain. The other common one, as I said, was this one, where you have either just a voltage, or you have, and then you always like use U of t with it, and so it's going to be 1 over s in the frequency domain. This is another common one where in the time domain it's an exponential function, which is what we saw with the one capacitor and the one inductor. And its form in the frequency domain is 1 over s plus a, whatever that a is, which is the number in the exponent. So without even knowing how to get these transforms, you can just use these tables and say, well, if my input signal is this, then the frequency transformation of this is gonna be like 1 over S plus A. Yes.
For the test, do we want to memorize these or
No.
have these in our notes? Like, will they be
No.
given to us?
Nope. I'm not gonna make you do any of this. You just wanna understand the process of this, and that's why I said you don't need to go into the details in chapter 12. What I'm gonna have you do is instead put the signal as a generic form. So just use V of S or I of S. And so you're gonna use just that you won't have to transform it. For those that have already taken the class where you're learning this, you can, if you want, do this and go back and check some of the other problems we've done and resolve them with Laplace instead and make sure you get the right answers. So it is a very good and helpful technique, and in 3500 you're going to go into more detail with those. Okay, so circuit elements. Into my that is bizarre. I can see it on the side, but it's not showing up there. Okay, we're gonna go here. So resistor is gonna stay the same. We already know it doesn't have any differentiation, integration to it. So in the time domain, it's gonna just be your voltage is equal to IR. In the S domain, it's the same. Voltage is equal to IR. What you're gonna see is the notation typically is gonna be a smaller case for time domain and then a capitalized letter for the S domain. So S domain and frequency domain mean the same thing. For an inductor, we have VL is equal to L DIL dt. If you solve that for the current, you have an integration. And one of the properties of the Laplace, which is really nice, is that you model the differential part and the integration by the S. So in this case, it turns out that just when you have a derivative, that's going to just equal S. And so you get SL times IL, and then you get a minus the initial value portion. So LIL of 0 minus. So for all of our situations, we are only going to look at when they've been sitting there and we just apply the voltage to it. And so all of our initial condition situations are going to be 0. So we are only going to look at the simpler case where SL times IL. So here, the impedance then is just SL, which is very similar to J omega L, right? From what we learned before. Okay. For the capacitor, same thing, we're going to have an initial condition is going to be 0, and then we see the 1 over SC. And so what you note from this is that S looks like it's the same as J omega. And that's because we're not taking into consideration the initial state. Therefore, we have no transient state, and we're only looking at the steady state. And so these are going to be interchangeable when we're looking at that steady state, which makes it really easy to manipulate the equations. Instead of a complex number, now we're just going to have S. I don't know where. Okay. So R goes to R. It's in the middle. That is really bizarre that my picture is not showing up. Which image is in the middle of them?
It's a resistor and then a capacitor.
Capacitor, okay. All right, so the capacitor is 1 over SC, and the inductor, cap, and then the inductor goes to SL. All right, so now looking back at the problems we've already solved, we can do the same thing. When we convert these, all we're gonna do is use like 1 over C and then S. And then here is just gonna be S times 10 milli. And so we would combine these again, which we did before, and take that in parallel with this one. So Z1 is going to be 1 over 10 times 10 to the minus 6s plus 1 over 50 plus 10 to the minus 3 s. Oops. And then plugging those in, it will this is easier to get an alternate form. So this is kind of the form you want to get it into. And you'll talk about this standard form in ECE 2250. And then you're also going to talk about the reason why we also want to get it in this form. So now from this information, you can actually get a lot of information about the circuit. You can actually look at this and figure out the roots of your system, which tell you a solution to your system. You can see if your system's stable, which is actually in 5615, you go more into the stability. But you can get phase shifts from this, and so it's really powerful in that it can give you a lot of information. So from this kind of gives you more of a generic equation in that we don't know what our omega is here. We don't know what the input is. So this also can be graphed and actually give us information by graphing it for every single omega. And you get a graph called a Bode plot. And on that plot, it can, again, give you more information about the system itself. So those are things you're going to do in ECE 2280, so beyond the scope of this class. What I want you to work on is just getting these equations, okay? So that's where I want you to understand how to transform it, the elements into, from the time to the frequency, and then the manipulation of the equations to just get an expression such as this. Okay, so once it's in the S form, you treat it just like any other variable. So you don't have to treat it like a complex variable. So you can multiply by S, you can, get the common denominator there and just manipulate it just like you normally do with just normal algebra. So that's why I tend to like putting everything in S, because then I don't even have to think about the complex portion of it yet. And then if I want to get more information about the specific frequencies, I can just substitute in that S equals J omega. And then at that point, I can change them to, in this case, I would want to change it to polar form on the top and the bottom. So then I could divide and multiply all of the magnitude. That would give me the whole magnitude of the system. And then I would then get one phase, and that would tell me the full phase change of this system. Okay. So again, the goal is to just get these expressions for now. Okay. All right, so go ahead and work on, why don't we pick a few? You guys choose. Somebody call out a number. We'll do 2 more. Which letter? D? Okay. So work on D and another one? E. Okay. Work on D and E and get these expressions for Z4 and Z5.
Where shape part is, there's the big glass window that goes down. Yeah. Yeah, just.
Went over. Okay, so for Z4, it's gonna be, 10 plus this over these two branches in parallel. And that should result in 20 S plus 100,000 over S, yes.
So I got the same answer, but it had like S times X in the answer. So it was like the exact same, but it was just S 100,000 plus 20,000.
Where did you must have an X in your equation somewhere instead of times? Okay, I was like, that's odd. You see where you have that variable?
Yeah.
Okay. All right, other questions? Did you guys get this? And some yeses? Okay. All right, great. So, as you can see, I'm not going to ask you to simplify this on the exam because this does require something like Wolfram Alpha. So, I may ask you something simple like, maybe I'll give an example of something I might ask, but I won't ask you to do a lot of algebra. For Z5, it's going to be this branch in parallel with those two are in parallel first, and then added to this, and then that whole combination is in parallel with the capacitor. So ends up looking like this. That Z equivalent is kind of messy, so I wrote it separate. And then this is what I got from Wolfram Alpha. So on this, you can see like the bottom is a third order, so you're gonna have roots in there. You can use that polynomial to then actually solve for roots, and again, you can use Wolfram Alpha or a different calculator to actually take the polynomial and ask it what are the roots of this polynomial. Those roots are then solutions to this system. Same thing for the polynomial on the top. You can again get what S is as far as an exact value for the solution there. So you're gonna have a lot of roots of this system. How many? 6? 6 roots. So, yeah. All right, questions about this one? Pretty straightforward, hopefully. No, not straightforward. Okay, so now let's look at finding like a voltage and something like the current. So on this one, you're going to do the same thing where you translate it into the frequency domain, but we don't know what the input signal is. So you're going to put the solution of V of t is going to be some function with S times this input V of S. And that's what you're going to want to express the equation as, okay? So V of t, VTH of S, you're going to have some expression, that's what you're trying to find, times V of S. So that's the form that you're just trying to find it in, okay? So go ahead and solve for this one. Okay, so you're gonna wanna solve this just the same way, oh, yes.
How did you input your equation into
So, let me talk about the equation first. So you're gonna use, that's weird. The same method. So use node voltage, it would be VTH over 3, VTH over 3 for those two branches. So these two branches, and then these two branches now have an S description. So the voltage over that impedance, where the impedance is just in terms of S. So it's gonna look like this. And then at V1, same thing, they two go out, and then coming in is Vs minus V1 over 3. Make sure you're very, very comfortable with writing node voltage equations, okay? To put it into Wolfram alpha, so I used X as VTH, A as V1, and B as Vs. I've noticed Wolfram alpha is just a little particular, like if you do a V subscript, it doesn't always calculate it correctly, so I've been doing it with just one variable as a representation for each one. So just that is x over 3, and then a minus x over 1 over 50 times 10 to the minus 6 s. So I just use s's in there, just like they are in the equation. A minus x, just double checking. And then for V1, it's a minus x over 1 over 50 times 10 to the minus 6s plus a minus x over 0.6 times 10 to the minus 3s is equal to that b minus a over 3, where b is Vs. And then I did also I in here because I wanted VTH and I of S in the end. So I also put that I of S was Z. And so that is just B minus A, Vs minus V1, so B minus A over 3. And that resulted in these. So the second form is what I'm going to want to use so that the S is in there. And it does that and, so that symbol is for and. So it's just saying x is equal to that expression and z is equal to that expression, and you can't have your denominator 0. And then a, which was V1, is expressed as this one, and s can't be 0. So, did you not get those equations?
I did.
You did? Okay. All right. So this is the answer if you want to write it down. If you did not get that, make sure you are comfortable to use Wolfram Alpha or your calculator, whatever other tool that you want to use and are comfortable with to get that. All right, questions on this? Guys good? Okay. All right, so this may be more something what you could do by hand on the exam. So see how this one goes. So if R is 10, L is 2, and C is 1/3, find IS. Again, IS will be in terms of just that generic form of VS. So this is where if you knew what your input VS was, you could get a particular solution. But if you don't, then you can still write the equation in terms of that expression times VS. Okay. I'm gonna change this to a different variable. X. Wrong one. So this would be your solution here. I changed the VS to be VX because I realized that that got to be confusing. So in this case, just taking the voltage divided by the resistances or impedances. So VX over 10 plus this becomes 2S and this becomes 1/3 S. And then you want to get it in that form I said that is a polynomial with a 1 as the highest order so that you can then find the roots of the system. The reason you want to make a 1 there is because you're going to then factor these to find the roots. So this actually has to do with your magnitude. So that 1/2 ends up meaning something different for this. So you want to make sure you get it in this form. So this is something I could ask you to do by hand and ask you to manipulate it to simplify it there. All right, questions on this? Is this straightforward? Yes, no? Okay, some yeses. Okay, this one, again, let's change this to VX. And this one, I'm going to change to VY. All right, so find VY of S in terms of that VX input.
So the capacity, 3 over S?
Yeah. So 1/3 S or 3. Sorry, yeah, I see what you're saying. Yay, nay, yay? Okay. Yes. So this has to do with solving, like, the next steps of solving this circuit. And so, or getting information, I guess, from this equation. So you're gonna want to find the roots of the system, and in order to do that, you need to make a 1 there to then factor it out. If you don't, then your magnitude actually ends up being different. So you wanna take this as 3/10 is kind of the constant number in the front. Because you can still find the roots of the system by plugging that into like Wolfram Alpha, but then it won't give you the magnitude correct, like for the overall. Because here the magnitude in the front is going to be 3/10. Does that kind of make sense? Okay. So I would, like, on an exam, I would accept, you know, the top one if you did that by hand. I'm just giving you guys kind of the next steps of what you're going to use in the next class. Okay. All right. Any other questions? Yes.
So on like the exam, if we were to do it with mode voltage, for example, you
Uh-huh.
get like everything just over S. Do you want to artificially introduce an S so that you get a square on the bottom? Because I did it a little bit differently than you, where I just did KCL for everything.
Uh-huh.
And I got like dy over 2s and dy over 3 over s. And when you want to, I don't know, like, what would your approach be with something like that?
Yeah, so you do want to try to get it into this form, but as I said, if it's too hard to do by just simpler algebra, then you're going to use like Wolfram Alpha or some other tool to get that equation better. You know, this you can do by hand. And so if you had something like this, I mean, yes, it is a simple multiplication to get that number out. So the s is no longer on the bottom. So you see that 3/s, you would want to just multiply that by hand. Okay? So that would be the level of difficulty I would expect on the exam. I think this is the last one. Okay, so find IL of S. And again, change this to Vx, just so there's no more confusion on there. Yes?
If we have the magnitude, like 3/10 over there,
Uh-huh.
what do we do with it?
So
What's it mean for us?
So what this would actually mean is what you are going to do next class is you're going to actually substitute in S equals j omega. And then you're going to plot it over all of the range of omega. And so you're going to get this graph. It's called a Bode plot. And so that shift actually is where, you know, you're going to start on the y-axis. So if it's incorrect, you actually get, and if it's an amplifier, it could be like the amplification that you're actually looking at. So 3 is way different than 3/10. You know, as if it was trying to be an amplifier gain. Does that make sense? So yeah, that's why you want to be careful about, like, where is this actual value starting. So that will become very important in 2280. So if it's an amplifier, it tells you the gain of what you have there. Yay, nay? Anybody get this yet? Okay. All right, so you're gonna, this is gonna probably be easiest by node voltage again. So left branch path is gonna be V1 minus Vx over 10. This one's gonna be V1 over capacitor value 3 over S. And this one is V1 over 20 plus 2S. So all of those are going out, so you're gonna sum them. And then IL is gonna be this branch current, which is V1 over 20 plus 2S. And using Wolfram alpha, you end up with my A was V1 and my X was Vx. And then L was IL. So L is V1. Oh, that was supposed to plug that in, wasn't it? Yeah, that didn't quite solve it all. Try again. Solve for L and X. L in terms of X. Okay. Take that one out. Okay, so this is the solution. Copy the whole thing to make sure my equation is correct. Okay, so I think my equation looks correctly. So this is then IL. And X is my Vx. So I would want to do the same thing and remove out that 10. Again, I'm not requiring it right now, but that would be what your next step would be in this. All right, questions? You guys following? Okay, that's all I have for today, so I think we'll end early. So make sure, so gives you time if you want to work on your quiz. So you have time to work on your quiz. Are there any questions anybody wants to have answered?